Good morning, professor, teacher, and fellow students. Welcome to our presentation. Our team number is 60709, and our topic is reconstruction of 3D model of blood vessel. Our presentation will be divided in 5 parts. What did you have for your breakfast today? I had fried eggs, a toast with butter, and a cup of coffee. Obviously, our lifestyle has been westernized, and so has our disease pattern. Let's see this graph. Same as the United States, the cerebrovascular disease and cardiovascular disease are the second and third biggest killer in Hong Kong. Millions of people die of this disease. These two important diseases have special features. They are sudden in onset, and they have potential for reverse. So, a rapid diagnosis is very important. However, our current techniques have limitations. For example, the 2D images can be challenging, and the 3D one, as you can see, it is easy to read, but it's time-consuming and need expertise. So, can we improve our techniques? Before I tell you the answer, we have to know about the pathology of vascular disease. After discussion with a medical officer, we know that vascular disease has only 2 problems. One is dilation and the other is occlusion. Let's see the dilation case first. This is the formation of aneurysm and an increase in radius. And this is the occlusion case and thromboembolic events and a decrease in radius of tube. So, the change in radius is the determining feature. And further management is greatly dependent on this feature. If we know it at once, the doctor can treat it at once. So, more life can be saved. In our model, we try to use a mathematical perspective to solve the limitations. If the limitation can be solved, more lives can be saved. So our idea is simple, but the impact is great. Now we have 100 2D medical images of cross-section of blood vessels. They are provided by Professor Robert Miller, and we will use them to build a 3D model of blood vessel. And before our calculation, we try to make the hypothesis. First, to consume each slice of blood vessel has 1 μm thickness. Second, to assume the blood vessel has same radius along its length, so there is no dilation or occlusion. Third, to assume the center intersect each lies only once. So the following situation is not accepted. For each slice, we have a normal vector which is perpendicular to the slice. And we have L vector, which is the direction of blood flow, and cross product of L and N, which is a direction of radius. Once we know the direction of radius, we know the maximum radius, and we can find a circle C. We denote this area as omega I. C intersects omega I equals C. Now we can start our calculation. First, to convert the 2D images into 512 times 512 matrix, MATLAB denotes 0 as black point and 1 as white point. Then, we find the boundary points. Usually, we use the polynomial interpolation to find the boundary points. But this time, because the boundary is not perfectly smooth, so it is not a good idea to use a polynomial interpolation because it will yield a high degree of order. So, we use another method. We find black point and check if any one of neighboring point is white. If yes, it is a boundary point. Let's see this simple case. This is a black point, and these are the neighboring points. Because one of them is white, it is a boundary point. Now we can mark the boundary points and interior points. For each interior point, we find the minimum distance to the boundary. We use this formula. XB and YB indicates boundary points, and XI and YI indicates interior points. And among all the minimum distance, we choose the maximum as the radius of the slide. Let's see this example. These two are the minimum distance, but we choose this one as the radius because it can draw a circle to contain most of the interior points. However, due to the resolution and the unsmooth boundary, there may be more than one center yield the same radius. For example, these points have same radius as this. So we take a mean over the centers, and the center is not an integer. When we know the centers of all the slides, we find a formula to connect all the centers. We use the Lagrange interpolation formula in this form and solve constant A and B. However, it is difficult to compute the system of linear equation of PA equals X and QB equals Y, so we use MATLAB to help us. It is a software, and experimental results show that the polynomial of degree 10 yield the least square error, that is this. And we use the notation of this. Because pure key is not a square, so we cannot solve this. And we use the following method. Multiply by P transpose and Q transpose to both sides. And then P transpose P and Q transpose Q is a square. And we use MATLAB to solve the system and get this data. And this is the curve to connect all the centers. After that, we construct the sphere. We use the sphere coordinates to construct the sphere. But this time we use MATLAB to help us because we just need to type the command into the computer. Then we can see the following beautiful diagram. It is a three-dimensional of blood vessel. Compared to the 2D images, we have different angle, and the doctor can see the blood vessel in different view. And can you see there is something wrong here? This is a occlusion area. To conclude, we successfully to use 2D image to construct a 3D model of blood vessel. And knowing the location of occlusion, the doctor can give an instant therapy, and more life can be saved. To improve our accuracy, Fourier series can be used. It is a mathematical technique used for signal processing. Lastly, I hope the techniques can apply to the case that is blood vessel intersects cross-section more than once. Thank you.